In this video, we're going to take a look at a couple examples where we are going to try to determine whether or not two continuous functions are independent. And so let's jump right into our first example here. So here, let's let f of y1, y2, so our joint density, be defined in this manner. Right, so that's our joint density. We need to show that they are independent. And so to show that they are independent, remember the thing that we will need to do is we will need to show that the marginal density for y1 is equal to, times the marginal density of y2 is equal to the joint density of y1 and y2. And so we need to go through and we need to find the two marginal densities for these two variables. Right, so let's find our marginal density for y1 first. So that marginal density for y1 is going to be this piecewise defined function. It will depend on whether or not the value of y1 is between 0 and 1, or if it's between outside of the range 0 to 1. But in either case, we integrate over all choices of y2, and we integrate with respect to y2. So this is dy2. And when our value of y1 is anything else, so up here we have our value of y1 is between 0 and 1. And down here on the second piece, we have our value of y1 is anything else. We're still integrating with respect to y2. That top portion, it ends up integrating to f of y1. We can change those upper and lower limits to 0 and 1 because everywhere else that density function is 0. So this is, we only have to integrate this with respect to y2 from 0 to 1. And so when we do that, we treat the y1 like a constant. So 6y1 is all a constant. So we're going to add 1 to our y2 power and divide by the new power. And so we get 6y1 y2 cubed over 3. And we're going to evaluate that with values of y2 going from 0 to 1. Right? And so when we plug in 1, we're going to get 2y1, and when we plug in 0, we're going to get nothing, and when we take that difference, we just get 2y1. And so our marginal density function for y1, it is 2y1, provided our value of y is y1 is between 0 and 1, and it is 0 otherwise. We need to go through and do exactly the same thing for y2. We need to find our marginal density function for y2. So we take our density function, 6y1, y2 squared, but now we're going to integrate it with respect to y1 instead of with respect to y2. And we do the same thing in our other piece. Integrating with respect to y1. And so that first piece, the top part, when we integrate that piece, we really have an integral from 0 to 1, 6 y1 y2 squared dy2 We are integrating, not y2, dy1. We are integrating this one with respect to y1. So we add 1 to our y1 power. We treat our y2 as a constant and divide by the new y1 power. And we are evaluating that with values of y1 going from 0 to 1. And so we get 3 y2 squared. And we'll get 0 in the other portion. And so our marginal density there is ultimately equal to, I don't know, 3 y2 squared, or 0, depending on whether y2 is between 0 and 1. And 0 otherwise. And so that is our marginal density for y2, and we notice that if we take the products of these, this marginal density for y2 times the marginal density for y1, if both y1 and y2 are in the range from 0 to 1, then the product there is going to be this 2y1 times 3y2 squared, which is ultimately equal to, which is ultimately equal to the 6y1 y2 squared. And everywhere else we'll be multiplying by a 0, and so we would get 0 everywhere else. So no matter the choice of y1 and y2, the joint density is equal to the product of their marginal densities. So we'll look at the other example in the next video. All right, we'll talk to you later.